In this video, we're looking at the central limit theorem. Now, previously we've talked about sum of samples and sampling distributions. This is sort of an extension on that. So I want to give you an example. Let's roll a die. You can get a 1 through to a 6, and each of which have exactly one way to do that. So if this axis was probability, then that would be like 1/6 chance of getting each number. This is what we call a uniform distribution. This is not normal. Normal distributions are bell-shaped. This is nowhere near bell-shaped. It's a flat line. Here's 2 dice. So the reason the shape looks like this is, well, there's one way to roll a 2. So you can get a 1 and a 1. When you try and roll a 3, you can get a 1 and a 2 or a 2 and a 1. So there's 2 ways to do that. If you're rolling a 4, you can get a 1 and a 3, a 2 and a 2, or a 3 and a 1. There are 3 ways to roll a 4, and so on and so forth. So the distribution looks something like this. Looks a bit not bell-shaped yet, but it's definitely different to the original one. And rolling 3 dice. Okay, that's starting to look a little bit familiar. The central limit theorem basically tells you if you do this process, no matter what distribution you start with, it will always end up being sort of bell-shaped if you do enough like sum of samples. So it's really powerful. It takes any data in the real world and basically turns it into a bell curve. It's also the don't put all your eggs in one basket theorem, I call it. And that's because like with sampling distributions, when you take the average roll of 3 dice, you're going to get a lot less variance, because for each of your like 3 dice here, you might have one high, but then a low one, and then sort of a medium one, and they will like cancel out. So your variance, the standard deviation, goes down. Really importantly, notation wise, I would call the first distribution here X. This distribution for rolling 2 dice, S2, the sum of 2 dice. And this distribution here, S3, the sum of 3 dice. So this is the total numbers. If we looked at the averages, so if we were like dividing by 2 here, I'd call that distribution X bar 2. And same, if we're dividing by 3, I'd call that X bar 3. So you might also notice that here, this is something we'll learn a bit later, but the mean is 3.5 there. Like with sampling distributions here, the mean is double that, so it's 7. And here, the mean is 3 lots of 3.5, so it's 10.5. Okay, so a lot of this crosses over with sampling distributions, but basically this is a full statement of the central limit theorem. So the mean will become n times the mean, and the standard deviation gets scaled up by root n. If you're dealing with x bar, which is the averages, the mean stays the same and the standard deviation gets smaller. Okay, this is another example. So this distribution, we would call it positively skewed because it's being like stretched out positively, not normal at all. But if we start looking at some sampling distributions, so this I would call x bar 15, x bar 30, and x bar 60, we can see that it just gets more normal. More and more normal, the more, the higher that number is. And the reason that I know this is x bar and not s bar is because it's sort of staying around the same amount, so around 3.0. It's just getting less and less and less spread out. Okay, another really common example is like grades in like a class. So you tend to see a lot hovering around the C or the A band based on like historical data. You do see a few Bs, but not as many as on the extremes for C and A. So for one class, this is not a normal distribution. But if I looked at this class and I took the average, maybe my average was sitting right there at like a, I don't know, B plus or something. Then we start plotting all those averages. So you can look at lots of classes. So this particular class may have got like a B plus. You might have another class which got a little bit less than that, maybe one that got a bit more. But even though each individual class is like not normally distributed, don't mind my dodgy graph here, when you start looking at lots of different classes, the averages, and you plot them all against each other, they sort of cluster up and become normally distributed around that sort of center point there. Okay, so we'll do an example question. The two histograms are W and W15. So notation-wise, this is like X and X bar 15. Which is W15? It is A. So it looks more normal. As soon as it looks more normal, that means this number is bigger. You can also think of X as the same thing as X bar 1, if you want. Okay, let W25 calculate the mean and standard deviation. So we need the original mean and standard deviation, 18.2 and 0.3. So the mean of X is 18.2 and the standard deviation of X is 0.3. And we're measuring in grams. So if we're looking for the mean, sorry, that shouldn't be X, that should be W. And W there. The mean of W bar 25 is the same, 18.2 grams. And the standard deviation of W bar 25 is 0.3 divided by root 25. So that sort of comes from the formula there, standard deviation over root n, whatever n is. Okay, so we can figure out what that is. Just jump in your calculator, 0.3 divided by root 25, 0.06. 0.06 grams. So you can see it getting small. Assuming W25 is normally distributed. Now, I want to talk about whether it's normal or not. W15 already looks kind of normal, so it would be reasonable to assume that W25 is. As a rule of thumb, n equals 30 makes me very happy. Or if a smaller n value was already normal. So if either of these two things are true, then I'm going to be happy. Things only get more normal the bigger n gets. So 30 will mean you're pretty much always fine. It's like a rule of thumb. Or maybe if the original distribution was already normal, then, you know, X bar 30 is also going to be normal. Okay, assuming this is normally distributed, calculate that. So W bar 25 is distributed normally. 18.2 is the mean and 0.06 is the standard deviation. Probability that W bar 25 is less than 18 roughly equals, okay, menu, stats, dist, norm, NCD. Our lower is minus a whole bunch of 9s, our upper is 18. Standard deviation 0.06, mean 18.2. Done. Execute. So 4.29 times 10 to the minus 4. If you want, that's roughly equal to 0.000429. So very small. The manufacturer sells these packets. Each box contains 25. The label says that. With reference to your answer in part C, comment on whether or not it is reasonable. Okay, so for the average weight to be less than or equal to 18, that would mean the weight of 25 is less than or equal to 18 times 25. And we can work out what that is. Okay, so if we look at that, 18 times 25, oh my goodness, it's 450. Therefore, the probability that S of 25, so the sum of 25, being less than 450, this is literally the same probability that the average weights are less than 18, which roughly equals 0.000429. So therefore, the claim is reasonable. as there is a 0.04% chance it is false. The chance that they're underweight is super low, like basically nothing. Now, I really want to point out that another way you could do this is you could look at S25. So the mean of S25 is 25 times the original mean of one thing. So that's 25 times 18.2. 25 times 18.2, which roughly equals, this is just like another way you could do it, using sums rather than averages. So 455. And the standard deviation of S25 is root 25 times the standard deviation of one original one. So root 25 times 0.3, which is 1.5. So S25 is distributed normally. It's got a mean of 455 grams and a standard deviation of 1.5 grams. And the probability that S25 is less than their advertised weight of 450. I would encourage you to actually pause the video and see what you think this answer should be. We do know what it should be. Anyway, if you do that, then pretty much it'll work out to be the same as the previous answer we got. So dist, norm, NCD, the upper is 450, the standard deviation is 1.5, and the mean was 455. And we should get 0.04%. Yes, we do. 4.29 times 10 to the minus 4, which is exactly the same answer that we got before. So this was the W bar 25 method. And then this was the sum of samples, the S25 method. So just be aware about how those two things are different. If we're asking for the average weight to be less than 18, that is saying the same thing as that the weight of 25 is less than 450. Literally the same question. With reference to the histograms provided, so this is what I was talking about before. So as W15 already looks normal, we can assume that W25 is more normal by the central limit theorem. I'm going to go CLT to shorthand, but central limit theorem. So yes, it's reasonable. If W15 looks really not bell-shaped, like if W15 looked like that, then we'd be running into issues. But W15 is already pretty much bell-shaped, so 25 is only going to be better by the central limit theorem. Really important that you say that, which theorem you're referencing.